So, okay, so this is the very last session for today, and we go deep into the NRAN space. So we're gonna have 3 presentations from European NRANs. Maybe after that we can have a 5 minutes, very short break just to prepare for the remote presentations, and we're gonna have hopefully two remote presentations from the US. So the first speaker is Michal from Cessnet. Please go ahead.
Okay, hello everyone. My name is Michal Hlinsky. I will tell you something about advanced architectures and services in our NRAN. So let's go on it. These few topics which I will present, and let's start. First, we try to extend mission of research and education networks, and here is some motivation to do so. First is use the full potential of global networking, because there can run more advanced applications run parallel to internet, and there are possibilities to create experimental networks, and because of it use resources more effectively. And the second motivation is to activate the interest of users of new services. It could be like these examples of what I have here. It's demanding real-time applications, remote control of instruments. It could be expensive laboratory equipment, so it's effective to share it remotely, and many other things. This was the main topic of CEF Networks workshop, and here is some recommendations from this workshop. There are points like provide reliable environment for innovations, and test and deploy leading edge technology which is necessary to run some advanced applications. I will skip on the next slide. There are more of it, and more interested ones. For example, the first one, ensure that new applications, for example like atomic clocks comparisons or ultra stable frequency transfers, are not blocked in an NRAN's environment. Investigate the possibilities for dark fiber testbeds in European scale. And I see you don't see nothing.
I was told to press this button, so now I'm pressing the button and it says transmission failed. So at this point, maybe I need some help. Can you please help us?
There is a
sorry about that.
Technical stuff is.
I think we should stop to do a video as it's supposed to be tested, but otherwise go to options and the yellow button. No, yeah.
I will go to options.
DVI. But that will stop everything. So better wait for Eric to come and fix it.
If you are an experienced user of that,
no,
maybe
exactly
you can.
not.
I don't want to
we can break it, but
ruin down your system here. It's gonna cost more money for TERENA to organize workshops here. So can you just try and?
I try it, but I think it's not problem on my side.
Great. And if I press the button now, done. Go ahead. Thanks.
I try to restart the presentation. It's better. So I think I stopped here, and the third one. Okay. Next point, investigate possibilities of alien wavelengths deployment, especially in international environment, which is multi-domain environment, and many others. So, extension of the mission of research and environment, research and education networks. Sorry. All these points I mentioned before result into need of development from current state, where there are separated experimental and production parts of network, and development can lead towards something called integrated facility. Integrated facility is available to users in form of facility as a service, which we are trying to do like this, and it integrates production network services, experimental facility services, testbed services, network fabric services, and so on. Enables potentially disruptive experimentation, keeping production network services running reliably, and share fiber footprint for all of its services. It's cost effective to share fiber footprint for both experimental or production services, and it can be do. I will proceed for it. So there is some development in the world, especially here, because you can find on Wikipedia this definition that the internet is global system of interconnected computer networks. Now it seems to that it isn't true anymore, because the internet is one application of that system, and there can be many other services. For example, here again there is time transfer, frequency transfer, or what I mentioned before. These services are probably part of the future internet, and photonic services enable to build of integrated facility. Here I have to mention disruptive services. What it is? A number of testbeds have been found in recent years. They are providing insulated environments dedicated to testing potential disruptive technologies. It's affordable for lambda testbeds and higher levels, but the goal of dark fiber experimentation is to prepare cost-effective use of dark fibers for research and education community, and this require to work with realistic traffic loads. First, design and testing. Understand risk and reach stable solution. There is the proved approach to build integrated facilities, which allows to share fiber footprint. And the second step is a long-term operation period with parallel running of experimental production services. We have one example in collaboration with Aconet. It's the comparison of atomic clocks in Prague and Vienna. Why is it important? Dark fiber experimentation is important because it brings freedom in experimentation on networks. There are many scientific, engineering and technical fields which can benefit on it. It can be some of these examples: metrology and physics and any other fields of research and scientific disciplines. Now I will tell something about integrated facility in CESNET. Here is the map of CESNET2 network. Orange lines are our DVDM backbone, consisting of Cisco equipment and our own checklight equipment, which is developed in CESNET and manufactured in CESNET license. Here is DVDM network in Prague. It consists of 234 kilometers of dark fibers, which is lighted by CESNET checklight equipment. So, integrated facility in CESNET, we are trying to merge experimental and production part of network. It is not cost effective to lease dark fibers and use it only for experimentation. It is useful to enable experiments on production network, and on the other hand, it is useful to enable production traffic on experimental lines. Also, we deploy our research and development results in our network. Thanks to this, we can verify our results and increase the strength of our facility in limited funding. Let I see. Here I have some examples of our technology. One interesting is single fiber bidirectional lines, which can bring some cost savings in construction WDM lines and connections to end users premises. We offer 3 services in the CESNET environment. Here it is. You can find it more details described in the link here. First is called CESNET Photonic. It's a photonic service. My colleague Jan Radil mentioned it yesterday, more detail. I tried to make fast recapitulation of it. It's an end-to-end connection between 2 or more places in optical network. It's described only by its photonic path and allocated bandwidth. It's a physical route that lights travel from the one point in the network to another, and there is no OEO conversion along the path. It's all optical path, fully transparent, independent on any protocols, and it can provide minimal latency, mostly based on latency of propagation signal through fiber, and practically no jitter, because there is no OEO conversion and no regeneration along paths, so there is no point where its jitter came from. It's a stable service, and with one challenge, because it has a limited reach, because there is no way how to regenerate the signal in a optical way. And thanks to these photonic services, we can provide our facility as a service to experiment and share fibers with production traffics. Here is some application examples. Jan Radio yesterday mentions it more than I have here. Most interesting ones is interactive collaboration, remote instruments control. I mentioned it before, so I will continue. Here is some ways to implement photonic services. It can be based on dark fibers or dark channels, or are all optical lambdas. Each have each have its positives or its challenges. Here is on dark fiber you have full bandwidth, you have freedom to deploy your own equipment, but it's expensive to lease dark fiber. When you use optical lambda, you can save on costs, and but you have limited in bandwidth and equipment and so on. Here is second Cessnet Lambda service. It's an end-to-end transparent service over a dedicated EVDM channel. It supports multi-domain and multi-vendor environment, provides huge dedicated capacity, and can guarantee a latency and jitter. We implement Lambda services thanks to our OpenDVDM technology, which we can deploy with low cost. And we can monitor our equipment with a monitoring system called CLMON. Here you can see how it looks. It's being developed in Cessnet. Still, it's being developed. It supports Checklight family devices. We are working on multi-vendor support. We are working concretely on Cisco equipment, which we have in our network. It can provide full alarm history and easy view of on your network on the interactive map, where you can click on each device and see alarms and history and so on. Okay, third service is called Cessnet Circuit. It's carrier Ethernet service, end-to-end Ethernet connection. We now offer point-to-point service only, and we are experimenting with multi-point solution. We are focused on multi-domain environment because there are localities where we have to lease services from other operators to reach the locality. In that case, we have to build E and NI interfaces and establish a multi-domain Ethernet service. We are building Ethernet services based on E over MPLS in our core network and provider bridging in access, and we are focused also on multi-vendor interoperability. We run our carrier Ethernet lab and we test equipment from many vendors, for example Cisco, Juniper. We have now some MRV equipment, HP, and some others. I don't know what the other is. right now. Here I have a schematic view on our solution. We find the simpler layer 2 switches which we can place in user premises and separate each services when at the end locality is more than one customer. It's good to have such piece of equipment at the end locality when we establish multi-domain service like this, because we can establish a maintenance endpoint there and can monitor entire service from end to end, because other operators in Czech Republic don't support Ethernet OIM, what as far as I know. So we tried this solution and it works well. We also experiment with layer 2 control protocols tunneling through these services. We find out one issue when Cisco tunnels ELBA protocols in default in this tunneling MAC address, and other vendors have different default MAC address, but often there can be edited or you can edit what MAC address will be used for tunneling, so it can be modified to interoperability. I'm sorry, with Cisco. Here is our Ethernet OIM solution. We use level 4 to monitor service from edge of our core network to the end locality through other operators domain, which is here shown. Oh, that's all. So thank you for your attention. If there are any questions, I see I managed to save some time.
Minutes, so if anyone has a question about the SAS Lite or the SAS workshop or stuff like that, please go ahead. Yep.
You said in terms of offering photonic services, do you have any engineering rules and like limitations on what kind of signals you can apply, like low bit rates? Would you need more hardband?
Probably I can ask Jan. Honzo? if you can answer, because he's an expert in this field.
Well, it was a very nice presentation. It said it offers the possibility to support photonic services. Yes. The freedom of spectral use. But are there also engineering rules on like what low bit rates can you support and interaction with on-off keying, for example?
Actually, we're doing some experiments, so I cannot give you exact number, but I think it should be again possible, especially for these low speed bit rates. So in principle, yes.
Okay, thank you, Jan. Some other question?
No other question, you can always ask them during the coffee break or over dinner. Thank you very much.
Thank you. So,
and we can move to Felix from Switch. And I had a nice dinner yesterday together with Felix and Walter and some other guys, and they have already started to discuss about the differences between the Switch network architecture and the SurfNet network architecture. So now they have the chance to to show that to us. Next speaker will be Walter from Seven. I don't have to do any magic, so I just let's see. Needs a bit confidence.
So your
Okay,
resolution
it
is
works.
really
Thank you. Good afternoon.
Otherwise-
My name is Felix Kugler from Switch. This presentation is given together with Willy Huber. So I'm talking about lower layers, fibers and optics. And first of all, I'm talking about the new network we're trying to build, and formally the project was accepted last week. So this means don't wait for any detailed concepts, things like this. We just present our vision, the plans, the goals, and the rough concepts. So I'd like to start with a little bit on the network like it is today, how we built it in the last 10 years, the goals, the ways we want to achieve these goals on the lower and IP layer. Okay, so I think this map is a little bit familiar to some of you. This is the fiber footprint of our network in Switzerland. I mean, Switzerland is a small country. Nevertheless, we have 2,500 kilometers of fibers, and you see a lot of rings or mesh or mesh, whatever. The red dots are our POPs. Our POPs are our customers. So our POPs are within customers' premises. We have about 60 of them. And you see thick and thin lines. It's all just fiber pairs, but the thick lines is what we call the core backbone, where we have DWDM, and the rest is just simple technology. On top of this fiber network, we have mostly an IP service, which is the most important thing we do. One thing which is a bit special, we have two major exit points, not just one, which has a lot of consequences also. And what you have to know is traffic is not evenly distributed over this network. So we have really hotspots in the Geneva area, Zurich, and recently also in the south of Switzerland we have very, very large computing centers there. So this is where most of our traffic ends. Okay, the network is quite old. Fiber infrastructure and optics is about 10 years or more. Nevertheless, it's running fine. The most important service we provide is IP access. You can have this from 100 megabit to 20 gigabit at the moment. Very popular also is a point-to-point or multi-point service, just Ethernet links, which we provide with EOMPLS. With this technology we have the resilience inside from the IP network. We don't have guaranteed bandwidth, but we do a lot of over-provisioning. We closely monitor the network, so we are sure it's a good quality. And so far our customers believe it. Then in theory we have a third service, which is Lambda service. You could have direct Lambdas. They are unprotected and nobody of our community uses it. We have 3 Lambda services for international projects, LHC, all coming from Italy, going through our networks towards Germany or CERN. Unfortunately, stability is not really as good as we like. It's unprotected and we have interruptions now. And this is surely one of the goals we have, to improve this. But mostly things are working fine, so why do we want to fix it? I mean, we have limited lambda space, but we never use more than half of the lambdas we have. The reason is quite simple. If you go to Zurich, for example, you can see on some Saturdays trams like this. Such a tram is 100-year-old and it's still running. You can use it. You can go from A to B without problems. However, I mean, it's not the comfort you are used today. It's a bit slower. There's not that many seats and it needs a lot of maintenance. And the same is true for our network. So it does everything we need so far, but it's a bit inflexible. There's no way forward. So that's why we have to remove the optical layer and make a new one. And in the last 10 years we have seen a lot of development also. Size has shrunk, optics are tunable. We have new modulation schemes which allow to go to 100 gig and below and above, and also optical switching, which is now available. So, about the goals. First, what do we expect in future? I think one of the problems we have is that we don't really know what's coming towards us. I mean, we have our customers, this is quite stable, but every year we get some new customers, most of them small, because the big ones are already connected. We don't know where the new customers will be. But what we see is that also small customers certainly need a lot of bandwidth. For example, they just don't rebuild their computer room, but go to the cloud or a commercial computer center somewhere, and they need connectivity. They need the same bandwidth outside which they had inside before. So a small customer with a 100 meg connection says, oh, my computer is 200 kilometers away, I need 10 gigabit. And this really happened to us at a quite unfortunate place. So we have to be better there. We don't expect many customers to use 100 gigabit in the coming years. We will have a few, but that's it. 10 gigabit will be very important, could also be more important if we can offer 10 gigabit protected lambdas. So for us, it's clear that we have to support this natively. And then we have something new. We have researchers in the field, and somehow they get high definition cameras or fancy things which produce a lot of data. Or we have an observatory in the Swiss mountains, and instead of sending people to the mountains, they want to sit back home or in a university and look into the stars and get the pictures back. That's why we need bandwidth at some strange faraway places. Our strategy on the optical layer, we want to upgrade all the DWDM infrastructure within the next 2 to 3 years. This means amplifiers, ROADMs, filters, compensators, whatever. Then we will light up as many lambdas as we need, and then we light up in future when we need something, where we need it, etc. And we really expect a very long life for this infrastructure. We hope it will be another 10 years. That's why we have to be very careful what we select. Also, the selection of the vendor is an interesting thing, because it works best if the vendor survives these 10 years, and it's not so easy to get this. And because we have strange ideas from time to time, we are interested in a vendor which is really talking to us even after sales, and where we could have a good technical contact. On the network layer, we see a more evolutionary approach. We are really believers in IP. We have a lot of routers. If you remember the map, all the red dots have routers. It's really an IP mesh. And we looked into other things. You will hear more about this later, but we still believe in this, so we will continue with these routers. We will go to 100 gigabit capable routers at a few places, but we are not in a hurry. Routers generally have a shorter renewal cycle, so this is more, we exchange every year some routers, so this is not as forced as with the optical layer. Okay, if we do everything new, there are things we want to improve compared to the last network. Of course, bandwidth reserves have to be much bigger, and that's not so difficult, because the first system we use now has only 16 lambdas. Today 40 or 80 are no big deal, and speed per channel is also much higher. Very important is flexibility. We need transparent lambdas between all the nodes, which was not possible now in our system. Rapid channel setup. A couple of years ago we had more than a half year to do this, because we had problems to get the components, but today with tunable optics it's no big deal anymore. And we want a system which auto-calibrates itself. Today we have to go to the different nodes, tune everything. That must be over. We want to improve stability. We had some problems recently with interruptions of fibers. and interruptions, it couldn't be fixed in a couple of hours. So that's why we will have some additions to the topology. Also, by having optical switching capabilities in major junctions, we could improve stability. And the last thing is we try to improve the coverage of our network to go nearer to possible or potential users. This is just a few pictures of misfortunes which hit us or nearly hit us recently. We really had one interruption, 6 days, because it was a construction site, a bridge which fell exactly on our cable, and it took them 6 days to fix the cable. Unfortunately, it was minus 20 degrees outside, and it was difficult. And the other ones were near misses. So our cable, for example, is inside here, and it survived, but it's just pure luck, and it happened 3 times this year. So it's always in the mountains, and that's why we are now building a third way to the south of Switzerland. Okay, so to the details. About network stability. When we started with optical fibers 10 years ago, everybody said, oh well, in the cities it's difficult because we have a lot of construction work and your fibers will be hit. And what we see is exactly the opposite. We never had a fiber break in a city in the last 10 years, but we have quite some interruptions on the long distances. So that's why we claim now we need 3 independent paths to these hotspots I showed you. And normally on the backbone we have just a 2-path resilience. And in cities we think in future that one single link would suffice. Then we have increasingly problems with power. Electrical power used to be very, very stable in Switzerland. It's getting a little bit worse. So we really try to keep up the whole network, even if you have a major power problem, for example in Zurich, which is a major hotspot. That's why we built a network to bypass cities like Zurich. And this would be our vision of the new backbone. It's quite similar to the old one, but we will add some little pieces of fiber between, and most important here, the third path to the south, which is an expensive one, but a very important one for us. And if you go back to the hardware, this is the SIC lines are the backbone, the core backbone as it is today. And you see we have 2 different types of equipment. We selected Sorrento Operating Systems 10 years ago and built these 2 lines. And then a couple of years later we needed redundant paths to the south, and then we didn't want to install this huge equipment. Found very small and neat boxes. It's BTI. Unfortunately, these are not very compatible, so we can't have lumber services through these 2 different systems, but it's a problem of the channel plans. And you have to know that all this network is based on bidirectional transmission, so we always use just one fiber. And this is something we have to change for the future as well. The new optical core shall have the same transmission gear all over. So only one system, and it should also cover the east of Switzerland, which was a bit neglected the last 10 years.
Do you have a shared risk group here, just like Géant, or it's different fibers?
Yeah, it's a little bit the shared risk. And I see I have two different maps, because on one it's a bit another way here. So these are 2 dumps. So one is along the highway, and 2 fiber paths are along the railway. The problem is here. If we lose power in Lausanne, this happened, then we lose everything. And that's why we try to make something like one fiber pair is going this direction. But this will take a little bit of time, so it's not done so easily. But this is in fact one of the larger risks we have.
How long is power interrupt in your network? How long can a power interrupt?
Yeah, I mean, what we have usually is battery-powered things which last 20, 30, 40 minutes. So usually, I mean, we are inside the university premises and they usually have no diesels. There are a few exceptions, but usually don't have. And if you have a large-scale problem, this can be many hours. And of course, if you lose power in Lausanne, nobody is using the internet anyway, but all the rest of the country wants to use it. So that's why it's so important.
I could imagine that you will put your amplifier on a large UPS, which lasts for 8 hours.
Yeah, but UPSs are also very cumbersome to maintain. That's our experience. So the best is if you don't have to carry it for ourselves. So we are working on this, but that's increasingly important. And well, with the new backbone, we have also all the interconnection points to neighbor NRNs on the core, which was not the case today. And for those who don't know, this is not a national research network, it's a regional one. It's Bellevue, it's the research network of this southern part of Germany. Okay, this is how we see our backbone. That could be, for example, Geneva and Lugano and Ticino. And because these are the major traffic hotspots, we will have a lot of lambdas just going from this hotspot to the other one. And we don't want to regenerate this everywhere, so we really want to have transparent lambdas. However, we need the ability to drop a couple of lambdas in all the nodes without regenerating all the other waves. And that's why we think that the photonic approach is a bit better suited for our case than things like Infinera, maybe. This also means that all switching below lambda level has to be done elsewhere, maybe on a router or something somewhere else. But we are quite comfortable with this. Key requirements, this may be a bit boring, 40 lambdas at least, maybe 80 or upgradable to 80. Definitely we need native 10 and 100G. So just 100G is just too expensive. 1,000 kilometer reach sounds a bit big for Switzerland, but if you have this ring and want to have full restoration, then we need this 900 to 1,000 kilometers. Auto calibration, so whatever we do, add or drop lambdas, it just calibrates itself, the system. Support for alien waves. We have a long tradition to use alien waves, and we want to continue with this. Then tolerance for optical signals outside C-band. We come to this later. And then, well, it's just a wish. I mean, we are quite late to go to 100G.
Do you really require in the near future super channels?
It says appreciated. I mean, if you can have it without a lot of fuss, why not?
But it would not be a hard requirement.
No, it says appreciated. I mean, we are right now just starting to really make the detailed plan. What is mandatory, what is not. This is a process, and we learn a lot from you. But the thing is, 100G to 400G is just a factor of 4, and if you see 40% growth means factor of 10 in 7 years, we don't know. We wouldn't decide on this, but if we can have it, or if we can have a technology which will probably support this because it's gridless, then it's okay. Just this.
All indication actually, I guess you will achieve 400G bit super channel bit.
100G is basic.
What I was hearing is if you go to 400G, you probably need something like a larger
1 terabit
channel.
maybe, but I don't think so for 100.
Mauer?
Just wanted to be sure you're talking at super channels and the optical layer. Right?
Yes, absolutely.
Because that's the main difference. Because that
Yeah,
will make a large difference to the upper layer.
Sure. No. What I was hearing is if you go to 400G, you need something like 75 gigahertz, something which doesn't fit.
It depends on the link distance a little bit, you know, and what OSNR. If the OSNR is large enough, you can do higher level phase modulation. And as long as you can deliver the OSNR that is needed, you may be able to support it. If you go to really long distances, then you may need more spectrum. So it depends a little bit on what distance you have.
Yeah, okay. But I think
I really want to understand. One thing is that you have a super channel which is really combining everything in synchronous mode. One thing is that you have a super channel because you simply put together the optical cells according to the specification and everything else. So I'm trying to understand exactly at which level you actually glue together the channels, how you do it.
I think that the notion of super channel was a bad idea. What I mean is just one channel with 400 gig.
Yeah.
One optical lambda.
Maybe if we're trying to explain something, I think when it says super channel, it's meaning more flex grid. It's not being dependent on the 50 gigahertz ITU grid spacing.
Yeah.
Yeah, because the other possibility is doing this with the channel, like you're doing with an Ethernet super channel, in which you simply channel things together. You actually have 4 by 100, and then these cells got remixed together at the end.
Yeah, that's not what I meant.
In a different way. I'm very curious if you inherited something from Ethernet, or you're actually proposing a half-pipe.
I think I made a fuss here. The only thing I wanted to say is, if possible, we want to have the option to use something else than this 50 gigahertz grid. I understand there are different types of ROADMs.
Just another question about the requirement for contentionless ROADMs. I mean, that means blocking-free switching. How much important is that in let's say, in the size of your community?
We don't know it at the moment.
Okay.
It says remains to be defined. The thing is, we don't really know it at this moment.
Okay.
And we try to move a couple of decisions to a bit further on. Huh? Yes, about economics, looking back, we get a lot more these days in terms of transmission power for $1 or €1. It's dramatic. I mean, what we paid for a 10 gig transponder in 2005 compared to a SFP Plus DWDM now, it's incredible. Maintenance cost, in my eyes, is about stable, and fiber leases, we pay nearly half of our money for the network to fiber providers. It's really a lot. And prices have gone down a little bit, about 30% in 10 years. And it's pretty clear it's not going down anymore. Because it's not just fibers between Geneva and Zurich, where there is a lot of competition. It's fiber to our customers somewhere. So we have a problem here, and we can't really fix it. The only thing we can do is make more out of the fibers, and well, one obvious choice is share fibers, or use fibers for different purposes. And at least what we are looking for is to have these core backbone links and regional links using the same fibers as long as possible. If we have a DWDM system, we just use a little part of the whole spectrum, including OSC. It's about 70 nanometers. The rest is just here, doing nothing. And our idea is, and we actually do this already in a few places, to add CWDM channels left and right, this goes very well, and you can use CWDM channels for local to regional connections up to maybe 60 kilometers. This works well, and we know that at least a few vendors say, well, it's not a problem if you do this, we support this. This should be possible. And it's also possible, yes, it could be used by us or our customers. And important, instead of these two channels, we could just have L-band as a whole, or we can have L-band services in these CWDM windows, doesn't matter. And the advantage for us, this would be part of the core backbone, 2 nodes, 80 kilometers apart. And then we get a new small customer, or we already have it on one of the fibers. And we don't want to spend the money for 80 kilometers additional fibers. So we just hook it up in the middle, have these passive filter boxes, and they are small. We can put such a box in a railway station in the basement. It's just 1 unit high. It doesn't need power. It's very easy, and it solves the problem. It costs us about 4 dB of attenuation, and our idea is to pre-calculate this. So wherever possible, we just calculate with these 4 extra dBs. Then the rest is about higher layers, and which will be presented by Willy.
Yeah, Felix asked me to add a few words to routing and switching. That's only 4 remaining slides. IP layer design goals. What we would like to achieve, or what maybe we also have today, is of course high availability. Then we do over-provision our network so that we can have more or less virtually no packet loss. We always wanted to have lowest possible transfer delays. That means also the shortest physical paths used. As Felix said, we provide IP services and also private layer 2 networks on our network. The network infrastructure is a mesh network. We have 2 main exit points, Geneva and Zurich, more or less at the extreme of our network. And the POPs are inside the universities. We do not normally have POPs in a city. We put the equipment into the university, and this has also some issues because it's a footprint and power issue. The university would not like very much if we come with a router or an optical switch that uses 1 or 2 racks of space. And our solution must scale to small and big sites in the factor, in the number of students between 1 and 100 maybe. There was a longer debate also within our group in switch routing versus switching. When you want to use shortest physical paths, you can either use IP routers, or shortest path bridging has been discussed recently, like Trill or IEEE 802.1AQ. We did test with Trill boxes, bought 3 Brocade switches that support Trill. And after those tests, the conclusion was that Trill is not a solution for a national backbone. So we are missing network management tools like ping and traceroute. Maybe you could invent or program other tools, but it's lacking interoperability between vendors. So Brocade will not interoperate with Cisco Trill. At least that's the case now. Maybe in the future it's better standardized. It's also difficult to provide layer 2 services on such a backbone. And it doesn't just scale for a national network. It's a technology for a computer room, I think. So we concluded that we will continue with our IP routed backbone. It's robust, proven, stable, and a well scalable solution. Of course, we will not have 100 gigabit routers at all of those red spots, but the smaller organizations will be connected on stub links with switches, of course, just to save money. We have to provide layer 2 services. Our users want them, and there is a real business case associated with it because they are willing to pay for it. So 10 or 15% of our income only comes from those point-to-point links we sell to universities. Those emulated layer 2 services like Ethernet over MPLS or VPLS, they benefit from a meshed backbone technology, topology, and so are rather stable. We also provide lambdas, mainly for higher bandwidths like 10 gig for the LHC community right now, maybe 100 gig in the future for certain experiments or special projects. We want to provide lambdas with protection in the future with a new network, definitely. We had too many interruptions, longer interruptions on those lambda services we provide to the LHC people. Yes, if you do something like virtual point-to-point links, we were more or less forced to introduce MPLS in our backbone because it was at that time it was the only tunneling technology that was implemented in hardware in the Cisco routers. So we have configured MPLS on our backbone, but we only use a very restricted address range for these layer 2 services. The rest of the IP services is just pure IP. And in fact, you would like to get rid of MPLS again, maybe. We can do in the future. Maybe there is another tunneling technique that encapsulates those Ethernet frames in IP. We would very much appreciate it. Then you have no need for MPLS protocol in the backbone. Only at the edge you would encapsulate the packets. Maybe this is an interesting use case for software-defined networking in the future. So we can implement our own protocols if the vendors do not do it. This brings me already to the summary of the talk of Felix and myself. So you have seen we will rebuild our network. It will only modest expansion of the fiber footprint, mainly a third high performance links over the Swiss Alps. Then we will completely replace the transmission layer, core backbone. We will put in a new DWDM systems. We plan for 10 years again, not only for 4 years. I think the DWDM system, the decision we make and the vendor we select will be for 10 years, I guess, again. And we would very much like to have on the same fibers coexisting services for these time people, or maybe to connect small sites with cheap technology. Switching layer must be simple, robust, and high performance, a routed IP network. We use over-provisioning, and we see no business case for bandwidth on demand at the moment. But as I said, the private networks are nevertheless needed, mainly for traffic isolation, not for bandwidth guarantees. So just finished just in time, I guess. Huh?
Yeah, thank you very much. Perhaps we still can have one or two questions if you have any.
Yeah.
Yeah, one question over there.
For Felix.
I have a question for Felix. There was some request, preliminary request for preparation of tendering. There was one slide. It's point to tolerate L-band transmission. If you can read this slide.
Yeah. Okay.
Yes. It is
this one here, yeah.
Idea, and I suppose very difficult request for all vendors, because it is simple to promise to you that it will be tolerated, but when you will ask deployment of equipment, design, each vendors are using some modeling system, and such modeling systems, I know, are not able to calculate with something optical, with some optical transmission in the L-band. So they are not able to use their modeling system for preparation of design.
Yeah, okay, but we are not asking for a system which works in L-band. The only thing
it
is...
was different slide. Toleration.
Yeah, okay, but that's what I mean. I mean, for example, this time
it's just allowing
distribution thing. I would like to have it outside the C-band. If it's inside the C-band, like it's proposed today, then I see a lot of problems with the vendor, because if he is responsible for the system, he doesn't want to have things in his range. But if we can move this outside, like our CWM channels.
So just we would ask a vendor to continue to support his DWDM system, even in the case we add something very funny outside in this spectrum. So it's similar to alien waves. When you add alien waves, you have to go to your vendor and ask, do you continue to provide support when we bring alien waves to the system? And this we did in the past with our vendor then, and it's exactly the same. But you have to ask in beforehand. Later on, once it's installed and everything running, they might not like to add to allow us to do funny things. But if you ask beforehand, I think that's important for us. We would like to have this freedom to experiment there with other equipment.
So can we just get this here now, and maybe you can discuss offline.
Okay.
So thank you very much for this presentation. The next speaker is Walter from SurfNet. In the meantime, I'd like to welcome our two remote speakers as well. Eric Boyd from Internet2 and Inder Monga from ESNet are there. So I'm quite happy we're going to have all the speakers that we planned for. And Walter is the next one. And I'm just wondering if I still have to do some magic with the video conference or not, but hopefully it's going to work. Ah, yeah.
No. Okay. So my name is Wouter Huisman, working for SurfNet. I'm working in the network service department, and today I want to talk about SurfNet 7, our new network which is being rolled out as we speak. It's a network architect workshop, so I thought let's go back to our roots and how we perform our daily job of creating a new network or creating a new design. We typically have those kind of simple questions in our mind when making your design choices. And typically for a network, as I see it, we want a scalable network. It must be flexible, cost efficient. Of course, we have a limited budget, and of course, it should fit all the requirements of the end user. But bottom line, we try to keep it simple. And so the next question is, what's wrong with SurfNet 6, our previous network? So we take a step back and give you a short introduction on that SurfNet 6 network, which we have been running since 2005, I think. So the first layer is our fiber infrastructure, which is based on leased fibers from different fiber suppliers. Currently, we have got about 11,000 kilometers of fibers, quite large. And on top of that, we put either a WDM system or a CWM system just to optimize, the use of the fiber capacity. And as shown in the right diagram, you can see the topology. The thick color lines are the CPL links, the core network with the capability of 88 lambdas in our network, and the thinner lines are the regional rings, which are typically using CWM systems, and with regeneration meanwhile. So it's quite fair distance. So you can't put amplifiers, but we do regeneration with a couple of wavelengths, depending on the local demand of the customers. Yeah, last few years we have optimized the original WDM system. We deployed a Nortel CPL system, but we have improved it by introducing WSSs, especially on the inter-ring locations. So, for example, this location, which is Delft, Eindhoven, Nijmegen, Zwolle, and also recently we have introduced WSS in Utrecht, and of course in our main location Amsterdam 1, Amsterdam 2, with flexibility to make a real mesh infrastructure across the fiber plants, and also making the paths as short as possible, so not backhauling everything to Amsterdam and then going back to the region if that connectivity was required, but you can then make the shortcuts as short as possible. So that's looking good. The next layer we have is our collapsed IP core. We only have 4 routers in the network. Sometimes we say only 2. One in Amsterdam, one in Amsterdam 2. And it has been upgraded during the recent years from a T640 to a T1600. And actually, as we speak, we are upgrading it to a T4000 with the end objective to merge the border and the core router into one chassis. So it's you're getting rid of all those inter-chassis links, which is then beneficial, and you have 100 gig capability as well on that router. The next layer is the transport layer. We built it on an SDH infrastructure, so it's based on the 6500 of Nortel, Shannon nowadays, and we transport light paths across that SDH layer. And as you can see, I made a diagram once. We have a city ring, it goes into a 6500, goes on the lambda CPL, it goes to another location, 6500, and again it's a city ring. And what you see is that it's a protected light path. It opens, closes here on a very small Gigi extended box, goes into a 6500 onto CPL. You may need some regeneration on particular sites, and that's how a light box is being constructed. And as well, you also see the flow of an IP service. It could also start in a Gigaman ring, city ring, also being handed over to an Ethernet aggregation box. Need a transponder chassis done on our WM system. So I think you already know or expect this is the layer we focus on to optimize, make it more elegant, more simple. So that's one of the main objectives of SurfNet 7. But another one, which is not really a layer in a network, but it's more a control plane, is our bandwidth on demand solution we have in a network. So we have got an Open Direct solution, which is it's a really standalone system. It has a GUI interface for the end user. It has an application interface, the NSI interface, so you can have an application making a reservation on your network, and it has then a reservation database, path computation, a nodal mediation interface, and then to watch your network. So actually it looks like you have got one network, but that's not the case, because you need to claim all the bandwidth you want to control with this network, and isolate it from the network which is being used for the static light paths, the light paths being provisioned by the NOC. So it's actually it's a 2-layer network we have, even though it's based on the same hardware. So these chassis are the same, but you need to split them up into 2 layers. So probably good for some improvements there. So what to optimize about SurfNet 6 and make SurfNet 7, yeah, simple. But even though we wanted to do all the nice things we expect from it. So SurfNet 7, the scalable network. This is the diagram which shows you all the layers I just presented before. And well, the first layer I already showed you. It's the IP core. It has been upgraded in 2008, and we're upgrading as we speak. So that's thumbs up. That's good. Next layer is the DWM system. It's also up to our standard at least, with all the flexibility we require. And the next layer is we want to address is then our service layer, which will be our next generation Ethernet network layer. So in the tender we had some concepts which would be required, which we expect from the network. Which we wanted a single technology for that carry Ethernet network. You should be able to provision it end to end from an NMS. Have the bandwidth guarantees we have in our SDH network, and yeah, that's an important feature. Another feature is, well, we try to reduce as much on power and boxes, so strip as many OEO as possible. Be ready for 140 gigs, so we can scale the network for the coming 5 years at least. And the last one, we really want to put the bandwidth on demand solution we had to the table. Say what can you provide us as a vendor? We don't want to do nodal mediation. We don't want the database stuff. You have got all the intelligence on that particular layer. Let us worry about authentication and authorization of the solution. But please, can you come up with a solution for that? So in the end, long and lengthy project. We came up with Shenna as our carrier Ethernet solution provider. It's based on the 5410 and some smaller boxes, the 3930 and the 5150. And we went into this technology agnostic. So we say, whatever you come up with, if it's equals our expectation, it's fine. So we ended up with a VBTE network, and well, we had the discussion: is it that, or is it not that, or is MPLS-TP the future? It's how it is, and actually it works as we expected. So it brings to the table all the features. We can provide all the services we want to create. So it's good. Well, the next step is, of course, after you have signed the contract, started planning your network. It's always a nice part in the network. So we ended up with a tiered network. So we try to make a schematic diagram. So this is these are the routers. We've got an express core network, which typically coincides with the interring locations, so the Nijmegen, Utrecht, Eindhoven locations I showed before. And in between those locations, you have got other core locations also with DWM connectivity, which makes this layer as is. And then finally, we have got some regional rings, which hook into those core locations or maybe an express location. And this is then typically CWM. Routing a service is very easy then. You have an end-to-end service, create a tunnel from here to the other side, and off you go. And obviously, since we have these express links, we try to reuse that express links as much as possible, so we get big fat pipes in the core. The next optimization is to use tunable XFPs in the carrier Ethernet switches. So we don't need any transponder chassis. It saves a lot of money and power and space. And the nice thing, during the tender process, Shenna came up with the OTN XFP, which has G709 FEC on it. So it's quite interesting because some links in our network are quite long, and you wouldn't be able to reach distance with a normal XFP. So you with the G709 wrapper on top of that, you can easily manage that. So that's about 25% of our links in our network use this OGN XFP. So one step back, we had an issue with SurfNet 6 also, because we had an issue with scalability, and scalability was caused by a couple of factors. We had, first of all, light path uptake was more than expected. We had, well, about 250 light path services with a significant amount of bandwidth requirement. And that's the next thing. By having an SDH core network, you really claim the bandwidth hard on your network. So any 1 gig service, it's taking that bandwidth away from your network. You don't do any reuse of the bandwidth, and well, as an effect, even though the bandwidth is claimed for 100%, it tends to not being used at all for, well, not for the 100%, or, well, you have those situations in which you only see a couple of megabits or hundreds of megabits, even though you have 1 gig reserved on the network. So there's a lot of bandwidth idle on the network, which is yeah, it's a waste of bandwidth. Another thing we also saw that especially in the larger locations, we run out of ports. So it's on the line card side, but also on the client port sides. So we need to increase the density of the ports. We did a first step, but yeah, you can continue with that continuously. But you also can think about maybe we can put some more servers on one port, and yeah, make it more scalable. It's also easier for activating a new service. So, well, first of all, statistical multiplexing. It's all too well known within this community, I think, but in our SDH network we would typically have to address at least this bandwidth on those 3 services hard, so it's gone, the bandwidth on your network, and aggregate that, and then you would have yeah, a situation in which you have, if you sum all the bandwidth, well, it's more or less like on that level, and you have a lot of overcapacity on your network. So one way we think we will implement light path services to define a 2-color quality of service mechanism in which we have a guaranteed bandwidth, CRR, colored green, and a burstable bandwidth, which could be, yeah, then of course we have to decide where to put this threshold. And well, we think by monitoring the 95 percentile, like it's also done with its IP networks, you could define this level, and you can also adjust it if required. And by that you have a kind of shared pool of EIR bandwidth on your network, which gives a lot of flexibility. So yeah, back to the single service port. That's something we will maintain in our network, but we also see a big benefit with the multi-service port. It would allow the end user to put IP services on that particular port, but also light path services and bandwidth on demand services. So and well, in this example we have shown you a 10 gig interface, and that's the type of interface we will supply to every university from next year on. So they can use that interface, and it's a fixed price, or actually it's included in their contribution, and they can activate those light paths free of charge. So that's the whole concept of the MSP. If you buy an MSP from SurfNet, you've got a free, yeah, you've got a port, and then you can use it whatever you like. And we hope to see an uptake in the light paths, but also on the bandwidth on demand light paths. And yeah, that's also the next topic, the bandwidth on demand. So we have well, Shenna, but also other vendors actually were keen enough to allow us to have an interface into their NMS system and make their NMS system calendar aware, so they can do reservations in future. And that makes the whole complexity of your bandwidth on demand solution, quite simple. You just need to put a call into your NMS with a start time, end time, start node, or start port, end port, and you have your light path. And that's more or less, in a nutshell, the solution we foresee with bandwidth on demand. We're almost there. So we hopefully, beginning of 2013, we have this up and running, and we already have this part is already implemented. It's actually now active, so you can use this part on our open direct system. So this is a really nicely developed last year with interfaces towards our Serve Connect solution. So it's for authentication and group management. And we have got the NSI interfaces and the GUI interface to make those reservations. Oh yeah, this is a screenshot of this application. Okay, so what's an elephant flow? It's a kind of department statement. But if you have the really big data flows, UDP maybe even, you want to make sure they don't push away all your traffic of other customers. So you must be careful about that. And the other thing we have, by the unpredictability of dynamic light paths, you need to be sure that you can address this within your network. So with all those, you really have to rely on the NMS and also on your equipment. So we at this moment are building our network on 10 gigs, multiple 10 gigs. So we have aggregations of multiple 10 gigs, and by that you create 10 gigs, 30 gigs links. Obviously we will apply 100 gig when available, but we certainly will have 10 gigs in our network because 100 gigs everywhere is too expensive. So our PBT solution works as follows. It has a layered structure, as we saw yesterday. It has a tunnel link capacity. This is this gray box. The tunnel profile with a certain bandwidth amount and a service bandwidth, which can, if it matches, it can be put into the tunnel. So it's a bit of a theoretical example, but if you have a 2-node network with a 10 gig link between A and B, you have a tunnel, the gray one, and then an existing light path or a set of light paths consuming all the bandwidth of that particular tunnel. You can't add another service to this tunnel. You first have to upgrade this tunnel to support more bandwidth. So that's the requirement. We want another 5 gigs of light paths. So you need to increase that tunnel first before you can apply that service. So if the NOC is doing what we call an RFD, request for design, the customer wants a 10 gig between the particular site, then they need to reserve the bandwidth on the network. So that's typically the action they've now performed. They've increased the bandwidth between A and B, so they can address the service in a couple of weeks' time. But the bandwidth on demand thinks, well, that's nice, I can put a service on that as well. So they claim a 1 gig service on that particular tunnel, and your static light path, which you thought you could provision on that particular section, is not possible anymore. So that's something, a kind of scenario which we run into when building a network and thinking about it. it's not too difficult to solve, but it's something you have to really address and also talk with Shanna how we do it. So the solution is make sure that dynamic light paths, bandwidth on demand light paths, are put in a separate tunnel. So make the NMS create a new tunnel for dynamic light paths. So you can't have that sharing of static light path tunnels and dynamic light path tunnels. And you should claim your bandwidth in advance. So as a NOC engineer, if you have your request for design, make sure you claim the bandwidth on your network, and it can be done either by creating a new dummy tunnel, saying that's the new 5 minutes, okay, yeah. Or increase the existing bandwidth on an existing tunnel. 2 ways to solve it. Another thing we have, it comes back to the link aggregation issue, is I made it easy explainable, the 2 elevated dilemma. So assume you have 2 elevators. We actually have it at SurfNet. Usually only one works. It's a bit of a pain. But and only 10 people can fit into the elevator. Otherwise it will ring a bell and it won't move at all. So you need to really apply to comply with that rule. So you have a group of people, lunchtime, coming to the elevator, but at the same moment there's another group, 5 people, and they want to take the lift to the 4th floor. And then it's the gambling of your hashing algorithm, whether it works or not. And in this case, you're lucky, so everybody can go up to the 4th floor. But of course, there's that other chance. In this case, only 50% chance that it works, that it that doesn't work, and you have an issue, and you will have in this scenario not packet drop but something else. So this problem, I rewrote it in the lag issue again, but you have with big flows in lags, and you have to be careful about that because you think you have 20 gigs worth of capacity, but that's not the case, or at least you can't be sure about that. You don't have any control on the hashing algorithm. It's typically based on the IP address or the MAC address, depending on what setting you choose. So we see this as a problem for lags if the physical link speed of your circuit is beyond 10%. So well, the easy fix is put 100 gig in place. That's easy fix but costly, and not always possible in certain more regional locations. Or otherwise, use lags, but be very conscious on the flows you put on those lags. And we split the lags in 2. So we've got a strict lag and a loose lag. And the strict lag is a lag only with one member, so 10 gig max, and it can accommodate any services, or use a loose lag, which can be a set of multiple link members, and it can accommodate light paths up to 1 gig and IP. Well, this is again a kind of work in progress, which we discussed with Shanna, and this is showing you the interface of the provisioning engine. So it's being implemented in the network already. So conclusions. So we have, I think, some clear optimization in SurfNet 7, end-to-end service provisioning on a single technology layer, tunable XFPs, which is a cost-efficient way of hooking up your carry Ethernet solution to the DBM system. Well, obviously the bandwidth on demand the bandwidth on demand now uses the NMS database and all the intelligence which is already in place. So it's you only have to worry about authentication and authorization. Obviously, we expect that we have less. At least we have better utilization of the core links in the network by using statistical multiplexing instead of SDH. And we really hope to see an uptake by all the new light path services and bandwidth on demand service by using the multiple service ports. And just highlighted some complications on how to secure the bandwidth in our network, and well, be careful with large data flow, single data flows, and which can result in unpredictable behavior if you're using lags. So that was my last slide. Any questions? Yeah.
So questions go first. Yeah.
The multi-service port there. How do you separate the different services? Is by VLAN tracking or anything else?
Yeah, VLAN. Yeah.
Just pure VLAN. So
yeah.
you will not. Don't you think you will run into something with the rate limiting the service later on the network? You need to have some per VLAN shaping, don't you? If you have assigned 2 gig of internet traffic and they exceed that, well, on the client port towards them, you probably won't do anything. But later on in the network, if you want to reserve the flow, how do you handle that?
Yeah, so for IP, yeah, that's a good one. We probably won't be rate limiting at the ingress, but we would do for light paths. We would rate limits just by having, if you want 2 gigs, you get 2 gigs. So really would limit it. Yeah, and all CIR traffic, so all the green traffic is really calculated end to end and being allocated in the database. So it's not in the network. It's database kind of administration, and that's how it can validate whether there's the bandwidth in the network or not. All ERR traffic, which is also IP traffic, yeah, they will be doing statistical multiplexing, and well, I think everybody in our community try to put sufficient capacity in the network, so packet drop is not acceptable. So that's the concept we really yeah, try to keep high.
Victor, the last question, please.
Fiber channel. Some people seem to want to keep using fiber channel because of the fast throughput, that kind of things.
Yeah.
At certain distance, let's say up to 9 kilometers. Are you going to? Is that service needed in your network? And perhaps the same question to switch. We have internally for data storage, we use fiber channel, and it's very cheap, but it seems an Ethernet.
Okay.
That's what people tell me.
Yes, so we don't have the requirement.
Also not for big storage. That's a storage that has to be at the same time the same data. That's why we need a fiber channel.
No.
They say.
Yeah, no. We had this question probably about 5-6 years ago. We had this question once or twice.
Yeah.
But it never really became an issue. They fixed it with either gigabit Ethernet. You can have that fiber channel to gigabit Ethernet converter boxes.
But they are very expensive and they only work at 1 gigabit.
Yeah, no, that's true. Yeah, probably is.
Not 10 gigabit.
Yeah.
So they're very expensive.
Yeah.
Okay, thank you very much for this presentation, Walter. And our next speaker is Eric Boyd from Internet 2, and we can see you, Eric. I'm just wondering if we can hear you as well.
Hello. Can you hear me okay?
Yes, I can hear you. I'm just asking if we can raise the volume here a bit. And you want me to drive your slides locally, is that correct?
Yes, please.
Okay, so I'll connect here.
Try to speak up.
I haven't actually seen the audience yet, so I don't know who's there, but anyhow, good morning. Or good afternoon for you.
Oh, yeah. Can you see your own slides?
Yes, I can.
Okay, great. So the floor is yours. Please, you have half an hour. Roughly.
Okay, thank you. Yeah, so I'm Eric Boyd. I'm sure I've met some of you. I work for Internet 2 in the Network Services Group. I've also worked in the CTO's office as well. So basically I'm going to talk a little bit about what Internet 2 is doing with software-defined networking, but I'm going to give a little context as we sort of lead into that. And by the end, I'll kind of go into some of the work that we're doing with Genie as well. If you could go to the next slide.
Yep.
So a little bit of background. If you look back, I guess it was 3 years ago, Internet 2 was basically operating a 10 gig nationwide IP network. And with the economic downturn, the U.S. Had a stimulus program. One of the things it did was it pumped a lot of money through what's called the NTIA BTOP program into the national backbone, the regional backbones, and the campus backbones as well. And so that really had a significant effect. So if we could go to the next slide. This one's kind of slow to load, so I apologize for that. But so basically, one of the things, this was kind of called USUCAN, kind of called NTIA BTOP, but the gist of it was Internet 2 ended up with a much larger network with, going from 9,000 miles to 17,000 miles of our own fiber for the most part. It's now 100 gig instead of 10 gig. And we have the ability to implement a software-defined networking solution as well, which is what I'll focus on mostly in this talk. It was basically a 2/3, 1/3 cost, but it ended up the national piece being about $100 million in investment over the last few years. And I think the number is somewhere between $1.5 billion and $1.5 billion if you look at what the total investment was, including the building up of our regional networks, which usually correspond at the state level. Next slide. What does that network look like today? We still have our layer 3 services. Those are sort of the blue dots where our routers are. Our layer 2 service, which is what I'll talk about mostly today, is shown by the red dots. Right now it's about, I believe, 14 nodes. That will grow. We expect to be roughly 30 to 35 nodes. And then our layer 1 services are available through our add-drop facilities, and we're also willing to convert some of those into layer 2 service facilities as well as we have demand for them. So that's sort of the picture of the map. The other thing you'll note that's new is what we call the northern tier, connecting Chicago to Seattle, running up through Minneapolis and Montana and the like as well. Next slide. So Internet 2 is basically at this point offering 3 sets of services: our layer 3 service network, and it's implemented on our layer 3 service network, our layer 2 network, and our layer 1 network. We also have our commercial peering service, and we also connect to a bunch of international exchange points as well. For our layer 3 service, it's built on 10 Juniper routers interconnected via bundles of 10 gig. Our layer 2 service, as I mentioned, it's 14 nodes today. We intend this to be a heterogeneous network, which is a change for us. In the past, we tended to pick a single provider, but then each regional network would pick a single provider and each campus one would. So the end-to-end path between any 2 U.S. universities was always heterogeneous anyway. So as part of our effort to drive the state-of-the-art, we've committed to deploying a multi-vendor solution. So we have Brocades in the mix today. We'll be adding Junipers into the mix in January, and we expect to add Cisco's into the mix sometime next year as well. We also have the layer 2 network we built last year based on NECs. We're keeping that as sort of our advanced test network, and I'll talk a little bit about why we would need that as we go forward. Next slide. So just 2 quick slides on the drivers here. One of the drivers is data-intensive science. It basically requires the previous speaker talked about elephant flows, the ability to transfer massive files amongst a set of sites. And basically what we're trying to do to address this use case is create this globally interconnected layer 200 gig network, but also support science DMZs as ESNet has defined, and I'm sure Andrew may talk about them a bit. And then opening up the network stack through software-defined networking. And if you go to the next slide, our other sort of use case here that we're dealing with is services for network research. Basically, we feel that the network research community needs access to an at-scale, sliceable network research infrastructure, where at-scale sort of means nationwide, not just sitting in a lab. And so we're working towards implementing what we call the full Genie API, on our backbone as well, and I'll talk about that further as we go. Next slide. So I'm going to kind of veer off a little bit and then come back a little bit here. Internet 2 in the past year sort of announced what it's calling its innovation program. And the driver here is sort of a recognition that, at least in the US, that whereas in the 90s a lot of the innovation was happening on the campuses, in the 2000s that sort of moved into industry, and the academic community focused more sort of on business models and the like. And we've been trying to sort of recreate that environment for innovation at the campus level. So if we look back to the campus story, you know, one of the components of that is sort of the dichotomy of bandwidth. So if you look back in the 90s, you know, we had 56K dial-up to most homes in the US, but we had 100 meg to the pillow in our dorm rooms. So the set of our students was essentially large enough to have critical mass, but offered a different networking technology than sort of the masses had. And so the kind of company that came out of that would be Facebook, for instance, which you couldn't have imagined in your 56K dial-up world, but you can when you do that. So we're trying to recreate that environment, so we're kind of trying to go for the ridiculous bandwidth environment again as well with the 100 gig network. The second thing is, you know, in the early 90s, folks were still building routers on campuses and the like, but if you compare that to today, you know, increasingly the routers that are out there are more and more black boxes that you can do very little with. So the second sort of aspect of this program is opening up the network stack. And then the third aspect is, you know, if you were launching a major research university today and building a network for it, and you were going to invite all these great scientists to come in, and then you said, but we're going to design a network for students on cell phones to look at YouTube videos of cats, people would kind of think you're nuts. And so, but a lot of US university networks are in a sense designed for that latter use case, not for supporting data-intensive science. And so, you know, along with the SNet, we're trying to really push the US community into enabling data-intensive science, creating the science DMZs, and really figuring out how to handle those gargantuan flows in an environment with many small flows as well. And these three components of our innovation program match up well with what we're seeing on a funding basis. The NSF has launched the Big Data Initiative, the CCNIE program, which is its first really significant investment in network research in a long time. And so there's a lot of synergy with what we're doing with sort of what's going on within the rest of the US. And this also matches up well with the Genie effort to create Genie racks, the US Ignite initiative to create new applications that take advantage of software-defined networking. So we've kind of been pushing this both on our own backbone, but then also into the regionals and campuses, and trying to create incentives for the entire US academic networking infrastructure to sort of lift itself up into this space. Next slide, please. So obviously this is, a lot of what I'm talking about is not just Internet 2 here. The NSF is playing a key role through its funding. We've had partners at Indiana University and ONRC, which includes Stanford and Berkeley, working with the Genie folks, working with the Internet 2 community to pull all this together. Next slide, please. So one of the things we've done is reached out to our campuses and basically asked them to commit to immediately two of those three pieces. Seems to be, there we go. Yeah, so you know, we talked a little bit about the fact that you need the Science DMZ on the campus. We'd like to see the campus connecting at 100 gig, and we'd like to see the campus embracing software-defined networking. And so what we've done is we've gone to campuses and said, if you can commit to doing two of those three immediately, and the third one over the next year, that's sort of our, you know, what we're calling an innovation campus, and our larger universities are really stepping up to that as well. Next slide. I think this is a duplicate. If we could go to the next one. So a little bit of history of where we've come from on this innovation side. We've been working with the Genie community, help them build what they call their mesoscale infrastructure, which is sort of before sort of the networks themselves were embracing this technology, sort of a separate network that was built through contributions like our Internet 2's Wave contribution, and the fact that we're operating several of the nodes. But it started to give people insight into how to run one of these networks. We've had a lot of engagement with our community in terms of saying that our community has embraced building an advanced layer 2 network with OpenFlow or SDN support. We demonstrated that we could do a 10 gig SDN enabled layer 2 service last October. We had additional push from our leadership to continue going on. Last winter, we issued a challenge to the vendor community with an RFP saying basically what we wanted to do. And we announced that we were going to build a 100 gig advanced layer 2 service last April, which we then launched a month ago at our fall member meeting. So we have a 100 gig SDN enabled heterogeneous advanced layer 2 service. So a little bit more about that. Next slide. So going back to sort of those campuses and how sort of we're taking that approach. So on the backbone we've got these innovation platform core nodes, and then we're trying to get the campuses to define their own SDN story, their own DMZ, and put their traditional campus network behind that as well. So this just sort of shows how we're doing that. We're also allowing people to plumb their layer 3 services through this network under separate agreements. And as we go forward in 2013, we're focusing more on virtualization and Genie support. Next slide. So this is just another slide sort of showing the Science DMZ concept that I've talked about. Let's go to the next slide. So a little bit about innovation themes. So as I'm talking through what we're doing, this is sort of the context of how we're making those decisions. The first one is heterogeneity is good. As I mentioned before, we had traditionally done a homogeneous solution, but then the regionals would do a different one and the campus would do a different one. So the heterogeneity popped up, but it did at the interfaces between the networks. So as part of trying to lead our campus community forward on this, we're putting those distinctions into the backbone and tightly engaging with the vendor community to make sure that they're interoperable from the get-go. If it doesn't exist, build it. We've been using open source controllers, but when we didn't find sort of an application programming interface sort of to sit above the controller, we built that, and I'll talk a little bit about that more. If it's open source, improve it. We needed something like FlowVisor to enable slicing on our network, so from a first cut, we started doing that. If it's in the marketplace, stress it and engage the vendors. We found the vendors very willing to engage on this. We have weekly meetings with the engineering teams at Brocade, at Juniper, at Cisco, etc. And we're basically running test suites against their code, their early code, giving them feedback on the functionality that seems to be missing, and working very closely with them. Next slide. We're also thinking about sort of, what's happening at the hardware layer, what's happening at the virtualization layer, what about the controller. OESS is sort of our name for the software that sits above the controller, the applications, and then interoperability in general. Next slide. So, we've rolled out our 100 gig advanced layer 2 service. So basically, as I mentioned, we basically demoed, so what did we do from last spring when we sort of announced that we could do it? In July, we basically demoed that we could do virtualization. Basically, what we were showing at the Summer Joint Techs was that we ran one application that had our layer 2 service that was in one slice. We had a second slice that was running Professor Code, Martin Sweeney's XSP application, the third slice that was running Indiana University Chris Small's route flow application, and maybe getting a name on that. And then in the fourth slice, we ran something we called the Nutty Professor, which was basically it tried to grab all the resources on the network. And we showed that using FlowVisor, we could lock that application down. We basically have had heavy engagement with the vendors. We've gone through multiple revisions of the Brocade code. We're working on the Juniper code. We've actually started now with the Cisco and Dell code. And we've got our nodes deployed and 1800 gig backbone circuits turned up as well. And we have our first customers on the network. Next slide. So this is a picture we put together for a Genie meeting, basically trying to show that we're blowing up the network stack. But basically what we want to be able to say, and now are able to say, is that basically we have a 100 gig testbed of innovation for tomorrow's internet open and available today. Next slide. So where are we trying to go with this? In some sense, what we're trying to do is on a common network platform, we're trying to build both our traditional services and our innovation services running in the same environment, and doing that on top of a software-defined networking substrate. Next slide. So I got a lot of questions at the Genie meeting and about, well, exactly, what is the software stack you're using to put all this together, and how does that interoperate with everything else? So this is basically the software stack that we're running today. We have the vendor switch, be it the Brocade or the Juniper, with the beta version of their software that implements OpenFlow on its northbound interface. We've adopted an open source controller, currently Knox, although we would expect that might change over the next year. Many of the vendors are trying to push their own controllers, but then essentially the northbound interface out of those controllers becomes sort of unique to the vendor, which in a sense, kind of breaks the whole point of the opening it up and making it a common API. And so we've written with Indiana University an application we call OESS that allows us to implement a layer 2 service on our backbone. And also the northbound interface out of OESS can serve as sort of a controller agnostic common API for multiple different controllers. And that's part of the Indiana University Center test suite now as well. So it has some likelihood of being able to work with most of the controllers that are out there. We've implemented a layer 2 service just on our backbone using the OESS UI, but that doesn't have any inter-domain component. We also took Oscar's, sort of the European equivalent of Autobahn, which implements the non-standard but fairly widely deployed East-West protocol, IDC protocol, and that's how we're doing our inter-domain today. There's also an Oscar's UI as well that you can use to provision circuits across multiple domains. So that's what we're running today. So next slide. Try to move quick here. We've been working very closely with Stanford on FlowVisor. I'm not saying that FlowVisor is a long-term solution, but it is a workable solution for us for the short term at least. It wasn't really production ready when we started working on it last May. We've been working very hard to make it something we feel we can run in a production environment. And so the idea is basically, I think of it as a one of many MUX. It speaks OpenFlow out of the north and southbound APIs. And the idea is that we can run our production layer 2 services in one slice and potentially down the line use the other slices for different things. Next slide. So one thing that's going on, and Inder may talk about this, is there's been a lot of good work by many of the folks I suspect in the room to build a protocol that's also a standard through the OGF NSI working group. And I believe ESNet successfully demonstrated an implementation of the NSI protocol at supercomputing, and so as that becomes available, we intend to deploy that as well, and over time you probably see some of the east-west protocol interactions for stitching together layer 2 circuits move sort of into that NSI domain. So that will be coming. Next slide. We've also committed, and this slide is not fully baked, so there's probably problems with this, but we've committed to implementing the full Genie API by May of next year on our production infrastructure. And so that can mean a variety of different things. If you look towards the top, some folks who are doing Genie experiments, really all they want are layer 2 VLANs, but rather than thinking of it as Oscar's East-West or NSI East-West, they have the concept of aggregate managers that, and Tom Lane gave a talk at the most recent Genie meeting talking about dynamic stitching, which is in a sense another flavor of the IDC or NSI that basically stitches together domains. And so we will be rolling out an aggregate manager as well for that class of Genie experiments. Perhaps more interesting or longer term, there are folks who are interested in doing their own controllers, etc. And or that traditionally, what sort of vertical, you can have an aggregate manager that controls sort of flow spaces, and gives you a slice. And so you could envision that we will be offering sort of the ability to run your own controller within your own slice. Now, we're not going to start with that on January 1st. Initially, we will very heavily vet anything before it goes on there. But our long-term intent, if we can make it stable enough, is on the same platform that we have our production services, is to also have experimental services where you have to assume it's a first draft of grad student written code that's probably going to break and try to hog all the resources. Next slide. So a little bit about our layer 2 policies. We're basically committed to extending a policy-free approach. You can think of each of those Brocade/Juniper nodes for our layer 2 services as functioning like an exchange point, or you can think of the aggregate of them functioning as a distributed exchange point. Next slide. In terms of our feature set, in the core, we have 10 and 100 gig dedicated ports, heterogeneous. We have full NOC support, and we've set up a whole test sort of QA infrastructure for doing testing as we try to test the interoperability of various vendors and their interoperability with our software. We have user VLAN provisioning through the GUI and backup VLANs as well. You can reach your layer 3 services. You can reach the international exchange points. And today we're doing inter-domain provisioning to IDC domains. Next slide. So what's coming is Juniper and Cisco. We're also rolling it out on Dell through our Dyn sites. We'll be adding virtualization via FlowVisor supporter. We'll be moving to OpenFlow 1.3 as it becomes available. We have multi-point VLANs. We'll be adding the NSI provisioning. Next slide. So I'm almost done here. A tiny bit about Genie. So today, basically, I talked earlier about that Genie mesoscale infrastructure. In the US, basically, folks are using the sort of academic networking environment to provision layer 2 VLANs through the campus, the regional, and Internet 2 to get to the Genie infrastructure. And essentially what we're trying to do, if you go to the next slide, is make, instead of using it to get to the Genie infrastructure, it just becomes the Genie infrastructure. So that everything that you can do on the separate Genie infrastructure today, you can just do across the backbone in our regional and campus networks as well. That's really what we're aiming for in terms of our partnership with Genie. So a tiny bit about where that is today. If you go to the next slide, you can see that the Genie mesoscale infrastructure has 5 nodes on the Internet 2 backbone, and they're sort of together in a ring, so they're quite reachable. And if you go to the next slide, you can see that coming in through our traditional ION network, which would sort of the IDC protocol over MPLS over our routers, you can get to that Genie infrastructure, or coming in through our advanced layer 2 service, you can get there as well. Next slide. We can skip that one and go one more. Yeah, so this is just sort of restating how we're doing our partnership with them going forward. And last slide. So, we're, in summary, basically where we're at, we've launched a 100 gig SDN-enabled network across the US. We expect to grow that to be about 30 to 35 nodes and be heterogeneous. We will be offering slicing, and we will be implementing the full Genie API going forward. Let me stop there. Hopefully we didn't go too far over, and I don't know if we have time for questions or not.
Thank you very much for this, and I think we have some questions. I'll try to repeat your question, or you can perhaps move forward closer to the mic, or just speak up. Or
can you hear me, Eric? This is Victor writes.
Yes, go ahead.
This question about Genie. There are European projects like the Sci-Fi project or the Future Internet project, and they are proposing something similar. For instance, HNet is looking also incorporating the Future Internet services in its own network. Are you going to cooperate with these Future Internet projects, or is it?
Absolutely. I mean, no. So I think there's sort of two ways to answer that. So the first thing is, we're kind of defining the Genie API as what we've seen today, but we fully expect that the Genie API will continue to evolve, meaning the network research community will continue to engage, and we fully expect that part of that engagement will be as the international collaborations between Genie and other projects around the globe come up with new ideas, that will be something that we're engaging with as well. So no, absolutely, we would like to be engaging on that. I should also say that we're putting together a new glyph task force on this. That'll be part of the glyph tech working group meeting, Techs in Paradise, at the end of the week in January. That's starting to look at the concept of what does interdomain SDN mean, if anything. So there's an effort to be putting together, to stitch together an international collaboration from Amsterdam through the US to Japan that's starting to look at that as well. So yeah, no, we will absolutely engage with the future internet stuff. We will absolutely engage through Glyph, but we definitely intended this to be an international engagement.
Thanks.
So thank you very much, Eric, again. Your time and efforts are appreciated. Thank you. And I'd like
if anyone has any further questions, just feel free to drop me an email.
Sure. So you guys just email Eric if you have more questions. I'd like to switch over to Inder at this point. He's our last speaker. And I'm just wondering if we can hear you, Inder.
Can you hear me?
Yes, we can. Great.
You have the slides. I can try putting it in presentation mode, but I'm not sure if that's going to work.
I can put up your slides, no problem.
Yeah, I think that's
good. Can you see them?
Yeah, I can see that.
Great. So please go ahead.
So I know it's a long day for all of you guys, so I appreciate you waiting up for this long. So I'm going to talk about software-defined networking for big data science. Next slide. So I think you're all familiar with, and as Eric talked, both of us have been marching towards a 100 gig network, and we announced that we have this backbone and working up and running by last week, and we hope to be off our current network by end of this month. So this is a new network. Doesn't look very different in terms of architecture from the ESNet4, but again, we had two networks before, an IP network and a science data network, which was a virtual circuit network. And with 100 gig, these are both combined. The big circles represent the 100 gig routers, but I will let you look at this network in piece in detail later. Next slide. So again, I think we have all talked about these problems. I'm not going to dwell on that, but I think the way we want to look at this is each problem is an opportunity for innovation. And so first one is this big science data flows problem, which we are all familiar with, and that's kind of something which drives our thinking and our reason for innovation. Next slide. And I think this community is very familiar with the global multi-domain science collaborations like LHC as well. And if you look at this complexity, this is kind of the workflows that we want our network to support, which is the reason for a lot of dynamic services, software-defined networking, dynamic VLANs, NSI, and all those things. But we need to see how we can make it easier for science communities to use the network to accomplish what they want. Next slide. So I think, Eric, I took a lot of my slides out dynamically because you mentioned a lot of them. So thanks a lot. The Science TNC, Personar, NSI, Oscars, 100 gig is the current reality, and and there is still a lot of work to be done to evolve them, and we continue to do that work as a community in Glyph and in OGF and standard bodies. So the software-defined slides I'll present is a forward-looking perspective, and I'm not saying that this is something that we plan to deploy, but it's definitely a strong direction that we want to explore. So kind of step back and put on your thinking caps, and hopefully you can give me feedback in this direction and see whether that makes sense or not. Next slide. So when we talk about software-defined networking, I don't know how clear this graphic is, but it seems to be like ordering pizza from a pizza store. There are so many options, and everything is software-defined networking, and anything we have been doing in this community, we can say, has been software-defined networking even before OpenFlow came into being. So it is a confusing time as to what that is and what that really means. But I think, we can say safely that it is something for everybody. If you go to the next slide. So what I decided to do was to take elements from Scott Schenker's talk, which he gave at the first Open Network Summit in October 2011. And if you guys haven't seen this talk, please, I have a link there. Please go and take a look at it. I think it is worth viewing it. So I'm going to take some phrases that he has in his talk just to highlight, what software-defined networking really means, and lay the groundwork for some of the ideas I'm going to present. So, so I think one of the ideas that has been heavily quoted and used is that we network engineers have the ability to master complexity, and that is why networking has been, in terms of what they say, a lagging science as compared to computer science and storage in terms of virtualization and the software stacks and the vertical, horizontal versus vertical integration. And I think what we have to say is that we need to now look at extracting simplicity. So the network is going to be complex. It is just by the nature of network, it is going to connect a whole bunch of things, and it is complex. But for the applications, what we need to do is to extract simplicity and present it to the applications. Next. And the way we extract simplicity and offer that simplicity to the applications is by doing abstractions. And we have been doing abstractions in terms of layers. I mean, if you look at the OSI layers, it is a form of abstraction that has enabled internet to scale. But as you look at the service layers and providing network as a service, providing bandwidth on demand, I think we need to look at a new set of abstractions or extend these abstractions. Next. And according to Scott Schenker, SDN is defined precisely by 3 abstractions, and one is the distribution abstraction, and I think this is what you're familiar with. OpenFlow and on software-defined networking architectures are logically centralized and not distributed like the internet applications or internet protocols were. But again, I have to stress it is logically centralized, and we have to keep that in mind. There is the forwarding abstraction, which is represented by the OpenFlow protocol and the flow forwarding. And then there is the configuration abstraction, and that is not something that many people talk about. So, next slide. So, again, I think going back to setting up the case for looking at abstractions, this community is very familiar with the fundamental network abstraction, which is an end-to-end circuit. And what that means is, if you look at wavelengths or PPP, point-to-point protocol, MPLS, L2TP, GRE, or even NSI connection services, this is an end-to-end circuit which connects point A to point Z and provides an abstraction to the end side that A and Z are connected. Now, A and Z are not directly connected, even though they give a vision of a wire. There are many switching points, store and forward, transformation of packets, VLAN translations, all going on, but it gives a seamless point-to-point and simple abstraction, and that has been very valuable for this community. So I'm not saying that end-to-end circuit abstraction is a wrong abstraction. It has been very powerful, and what we have done is we have made this provisionable. But what we really are trying to do in ESX is trying to say, given this new paradigm of network virtualization and abstraction, what other abstractions can be used given the problems that we defined, the 2 big major problems that we want to focus on. Next slide. So what we are looking at or investigating or experimenting with is a network abstraction of a WAN virtual switch. So if I could represent the whole wide area network as one switch, which is simple, multi-point, and programmable. Now that is the concept that we are pursuing and seeing the viability of it. So if you look at this from a Scott Schenker perspective, this is what is I would call the 3rd abstraction, the configuration abstraction. So instead of taking a traditional software-defined networking approach where you are aware of the whole topology and the application programs flows, you know, hop by hop by hop. And if you want to create a VLAN, you have to configure them and you have to know where the VLAN translation needs to happen. This configuration abstraction expresses the desired behavior. I want to connect 3 sites together and I want them to be able to talk to each other. I want some of the flows to be multicast, some of the flows to be multi-point, and some of the flows to be point-and-point. Few flows need QoS, and that behavior is expressed through this virtual switch. But the implementation of this, whether you put what kind of switches you put, is it layer 2 switch-based infrastructure, layer 3 switch-based infrastructure, or a layer 1 software-defined network, it hides that implementation and enables a multi-layer software-defined networking approach, which I think is what's happening and going to happen in this industry. So it's not a concept, but we have an implementation that we demonstrated at Supercomputing last week. So let me explain this abstraction a little bit more, and then go into the demonstration and the implementation aspects of this. Next slide. So just to highlight this a little bit with an example, is that you can take the whole ESNet, create a WAN virtual switch, and connect, say, the 3 leadership computing facilities together, Argonne, Oak Ridge, and NERSC, and have supercomputers exchange flows between them and define which flows they want to get switched to which facility. Next slide. Now, one of the interesting things about this virtual switch is you want to give control over the network to your end sites. Now, the way we have given control so far has been through a web services interface, the NSI interface. The other approach we are looking at is to give more granular flow-based control to our end sites. And the way we are exposing that is to take the virtual switch and have the virtual switch be an open flow based virtual switch. So the end sites or the clients, the customers can run an off-the-shelf open flow controller like a POX or a NOX or a FlowWiser and be able to direct their flows using a very simple, not having to understand the full complex network topology, but a simple network topology of a switch. And you leverage this protocol, this standard protocol, for directing flows and then abstract the implementation of it in the network. Next slide. So what do we mean by programmable by end sites? So if you take a multi-domain wide area network, and we as a community know how to do multi-domain really well. Next animation, please. And you connect 3 sites together into this multi-domain network. Next animation. You create this virtual abstraction of a WAN virtual switch, one switch that connects these 3 sites together. Next. And then each site has an open flow controller that it talks and directs its flows, and it can build its own applications, and then it can then program the flows. So site A can say, hey, for science flows going from A to B, this is the flow entry, and it can enter those flows into the WAN virtual switch, which in fact diverts flows from the edge of the network across the multi-domain to the other edge of the network. And as OpenFlow 1.3 gets implemented, you can specify a QoS, you can specify an MPLS label, you can direct flows at some point from A to B, sometimes from A to Z, A to C, and you can sometimes, depending on what your application is, program a multi-point flow, a flow going from A to B and C. And that replication of that flow happens within the network, and the end site doesn't have to worry about that. Now, this, again, it sounds very simple, but this is the simple abstraction that the end site sees. It sees it is able to program the wide area network as well as program the flows. Was there a question?
No, go ahead.
Okay. Okay, so Next slide. Now you might be thinking that, hey, one WAN virtual switch for the whole wide area network and all the people. No, that's not true. It is not that you need to now create a virtual switch which, millions of ports. It is meant for collaboration, so you can have different instances of the WAN virtual switch depending on which collaborations want to talk to each other. And not only that, each site can be connected to a different WAN virtual switch, and it is possible to do that with using the flow space and the flow space division or slicing that both Eric Boyd talked about and the Genie has been working with as well. So let's get to something more tangible from this abstract concept. Next slide. So for the supercomputing demonstration, we installed 3 switches, NEC switches in LBL, Argonne, and Brookhaven, connected them over the ESNet5 network, and we had a Sienna 5410 OpenFlow enabled switch at the Sienna booth where we were doing the demonstration. We connected 4 DTNs or data mover hosts to each of these switches, and we also leveraged the Brocade which was part of the SRS OpenFlow network, and as we were an SRS project. So this was the physical topology that we used to demonstrate the concept of the WAN virtual switch. Next slide. So what we did was, we have an interface where basically the end site or the application say create virtual switch. So you can, it's a programmatic interface since it's all about software defined networking, and an end site can say, tell the WAN, hey, create a virtual switch for me. I want these 4 ports and these 4 sites to be part of this virtual switch. And what you can specify, so if you buy a switch from the market, you get ports, of course, and you have a backplane, which if you buy an expensive switch, it is a non-blocking backplane. That means you have a full mesh of, say, if it's a 10 gig switch, 10 gig connectivity between any port, any to any port, and that is just burnt in. But with this virtual implementation, you can specify what kind of backplane topology and bandwidth you desire. Then you can specify the policy constraints like flow space, like this is the slice that my switch needs to control. And not only that, you can store this whole config in a topology service, like a personal topology service. So you can basically say, this is my switch, and I can instantiate that switch on demand. So not only like we do circuits on demand, we can instantiate the switching service on demand, say from 8 to 12 p.m. And you can put all kinds of on-demand semantics around this abstraction as well. Now the good part about this is one of the biggest issues I have when I talk to the network engineering folks. They say, well, SDN is not ready for prime time. I'm not going to change my whole infrastructure, and we just spend so many millions of dollars and now buy OpenFlow devices to replace them. This approach allows you to put OpenFlow enabled ports at the edges while supporting the existing infrastructure in the core. So you have an TLS based core or an optical based core or a PVT based core, you guys can keep that. Don't have to do a full change of infrastructure, but by putting this virtualization with OpenFlow enabled ports at the edge, you can give an OpenFlow interface to your customers without doing an overhaul of your network infrastructure. Next slide. So what does that mean in terms of software? Peter, this is in animation, so if you don't mind going one by one.
Sure, yeah.
So if you take the wide area network, and in this case, as in SRS, we had 4 switches. So you have the 4 OpenFlow switches at the edge of, a dynamic wide area network. Next animation. So what we have is we have a network-based flow visor to partition the flow space on the OpenFlow switches, and an Oscars-like service to create the flexible backplane between the switches, giving an appearance of a single switch. Next slide. Then we have a software implementation of the virtual switch, and that includes an OpenFlow controller to talk to the OpenFlow switches at the edge, and an Oscars API to talk and create the backplane. Now this virtual switch application exposes a standard OpenFlow based API. Next animation. And now, since we said each customer can, or each end site can slice their bandwidth into the wide area across multiple applications, we have a concept of a customer-based flow visor where they can partition and connect to multiple WAN switches. And then on the end side, they have their own OpenFlow controller, and they can write their own software-defined applications on how they want to use the wide area connectivity that they have and manage it themselves and be dynamic, while the wide area network provider has developed a software and a system so that they don't have to worry about the control of the end site. So in the end, if I look at these three layers, there is an infrastructure, software, slicing and provisioning layer, there is a virtual switch software stack, and then there is a policy isolation for the customer, OpenFlow control. Next slide. And this is an example of how it works from physical to reality. I'm walking towards the slide because I want to see it. I don't know how clear it is. Should I walk through this, or is that something you guys would want to walk on your own?
Can you guys do that on your own, or do you need some? Yeah, perhaps they can do. So you can just go ahead with the next one.
Yeah. So I'll basically I'm just going to talk high level. In the end, what we're saying is how does this virtual abstraction translate to physical, IP and what we know needs to happen. So you talk about a ping, you see OpenFlow packet in going up. The virtual switch acts like a switch and needs to ARP. It broadcasts the ARP over the two interfaces, so it's not a total wide area network broadcast. And then you can see the ARP response come, and then the flow entry is put on the OpenFlow switch, and the ping happens end to end. So it's you can see how easily we go from a physical implementation to the virtual switch implementation. Next slide. Just do all the animation for the slide here. I'm just going to talk through it. So basically, yeah. So in the end, what we're seeing is we have an end-to-end data plane. We really need to move physical bits, and you can never get away from that. You cannot virtualize moving physical bits. You still have to have photons. But on the end, we have created a programmable service provisioning lane. So we had a network services plane in NSI. Now we have just made it programmable. We have the NSI interface for going multi-domain. But in addition, what we have created is an abstraction of a virtual switch that can sit on top of this multi-domain point-to-point circuit architecture. And then using policy and isolation, what we have created is the customer or user control plane through which they can control the flows and the behavior across the wide area network, and they don't have to do it at the edges. Next slide. So we think it is a powerful network abstraction, and the reason to invest and think about network abstractions is because we have seen in the computer world the file abstraction has been so powerful to allow storage to scale. So you had directly attached storage, which went to network attached storage, storage area networks, storage virtualization, and all of that was possible because you had the file abstraction. And that file abstraction made sure that your applications didn't have to change while the whole network storage infrastructure changed underneath and how you did storage. Similarly, these abstractions, these powerful abstractions of both NSI and the design virtual switch, in our opinion, will enable the networking infrastructure to evolve independently of the end sites and how they use the network infrastructure, allowing them to invest in programmability with knowing fully well that even if the network infrastructure changes, their programs don't have to change. And I think that's why it's important for us to think about abstractions and in the wide area network. I think the benefits of this abstraction is it is simplicity for the end site. A single switch is much easier to deal with than a complex topology and them having to do pathfinding in order to know where to put the flows. It works with off-the-shelf open source controller. They can write generic code and And this virtual switch can be layered over optical, routed, or switch network elements. So you don't have to be tied to layer 2 packet networks. You can run this over a transport open, SDN or a routed open flow based network. You need open flow support at the edges only. So if you have investments in legacy infrastructure, you can keep that while still providing programmability to your end customers. And it allows the end sites to innovate independent of your evolution, and that abstraction, like file and storage, is going to be really powerful. Next slide. Now, in case you wanted to deploy it in your network tomorrow, and I can see the excitement in the room, just kidding. In case you are interested in this, I mean, this is still early days. There is a lot of future work to be done. We still need to harden the architecture and the software implementation to move it from an experiment to a test service. And we hope to have the test service running in ESNet. We want to verify the scaling of the model using virtual machines, simulation of many virtual machines implementing this model. We want to automate this intelligent provisioning over multi-domain and build wizards for making a virtual switch provisioning happen. And then we want to create recurring abstractions. What I mean for that is, if this abstraction works over the wide area, why can't this abstraction work over the campus? We have all struggled with getting dynamic services into the campus. Maybe this abstraction in the campus can allow easy, this abstraction and implementation in the campus can allow dynamic programmability in the campus as well. And then we have to deal with network of virtual switches, but that's a problem and a solution for another day. Next slide. Okay, a lot of people in ESNet help these in this concept. This is just not me alone at this, and I'm grateful to a lot of people who helped do this demonstration in SC12 as well. Next slide. That's about it. Thank you for listening at the end of the day, and any questions, I'm happy to address them.
Thank you very much, Inder. Questions to Inder? If you want to ask a question, please move forward, or just speak up.
It's very interesting.
Yeah,
absolutely.
It is a very interesting concept that you have presented with this abstraction, and I think we have to.
And certainly that you do it on the edges, I think, will help. So I'll look into it. Thanks.
Yep, we really have to digest it. So thank you.
I understand.
Thank you very much again, and thank you for your time, and have a happy Thanksgiving over there. See you.
Thanks. It's turkey time for us.
Yeah, okay. See you. So thank you very much, guys, for your patience. And yeah, tomorrow at 9:30. Okay. Let me just maybe I can show you the agenda. Where it is. It's here. Okay, so 9:30 tomorrow morning, and the dinner. Where's my dinner link?